Okay, so the hot water in that beaker versus a little bit of water in the pipette. So it measures the total, it's talking about the total amount. So that's why we have to take into account all the particles in there. Okay, also, when we'll talk about heat transfer here in a second. But that's what it measures. So if we take particles, we'll just show 3. I'm not going to get carried away. And then here, okay, which side has more heat in it? The right or the left? Okay. As a comparison. What's their temperatures like?
Right side's higher than the left.
Okay, why do you say the right is higher than the left?
The particles move around more.
What's that?
The particles move around more.
Okay. I tried to, I don't know if I did a good job of it, I tried to make them the same length. So let's say they're all the same length. Which one has a higher temperature?
More heat.
This side has more heat, but what's the temperature of the right side, this side, versus this side? Should be the same. Right? Aren't they all? If I take the average, all right? Say I take this length. Let's say this is this represents the energy of it, and I'm just going to measure the length because it's similar to it. So I go. This is 1 inch, 1 inch, 1 inch, 1 inch, 1 inch. 7 inches. How many do I have? I have 7. 7 divided by 7 is what? 1 inch. Okay. Here I have 1 inch, 1 inch, 1 inch. I got 3 of them. So 3 inches divided by 3 is 1. Same temperature. Okay. And the idea of that pipette and that water was that example. Does that make sense? So that's the thing that students kind of get mixed up. They think temperature and heat are the same. They're not. Temperature is the average motion of the particles. Both of these have the same average motion. Because of the length of the arrow kind of shows that. Okay? Temperature measures the average kinetic energy of the particles. Okay? So which one has a higher temperature? Right side. Okay? Low temperature, high temperature. Okay, so which one would have more heat energy? One on the right or one on the left? The right. It's a higher temperature. Same number of particles, but higher temperature. So it would have a higher amount of heat. Any questions on that? Okay, heat transfer is always going to go in the direction of warmer to colder. So heat is always Okay, and this is an example like by the window. Okay, by the window, what'll happen is the window tries to warm up, but the particles next to the window will give the energy to the window, but because they are doing it, they'll slow down and the window will try to heat up. The trouble is it won't heat up much because it's facing the outside cold temperature. And it probably won't warm up because there's not enough energy in the room to do it. Okay, so let's say that this object is hot. This object is cold. Okay, we're going to take and pour. Let's say this is a liquid. We're going to pour this liquid into there. Okay, so we're going to put the two liquids together, and the result of that is going to be a container. What can you tell me about the length of the arrows? Yeah, the colder is going to increase the size, and the warmer is going to do what? Decrease. And so we're going to have 6 of these in here. That's going to have a temperature in between, right? Does that make sense? They're going to be in between. And so heat is always transferred from the warmer. The warmer is going to speed up these, and they're going to give energy to the slower atoms, and because they're giving energy to the slower atoms, they're going to slow up. Okay, just like the vehicle. The vehicle hits something, it's going to slow down. That's that momentum type of thing. So, okay, and the last thing we'll do, I got a simulation here I'll show you. So you guys can do with what you want on this one, but I'm going to go ahead and show you the simulation. Okay. So if you want to draw something, you don't have to show as many atoms. I'm not making you show as many atoms. So in the first box, that would be a solid. I can show you different ones. Here's argon. Here's oxygen. Here's water. Now water is unique. Do you know what's the difference between oxygen, solid form, and water?
Water goes from liquid to
Yeah. But I mean, just look at the structure of neon, argon, oxygen, and these are all solids, and then we go to water.
They're not as connected.
More spread out.
Yeah, they're spread out. And if you notice, they kind of form hexagons. If you look at they kind of... So, have you ever seen a snowflake and it's kind of got a hexagon shape to it? Also, what do we know about water when it freezes?
Expands.
Expands. Look, it expands because it forms crystalline structures that are kind of spread out. That's why water's density is lower than the liquid form. Now I'm going to do a liquid here for water. And we'll look at the difference. So there's the solid form, and here's the liquid form. Look at it. They're closer. So the density is going to be bigger. So solids, when they form a solid, it spreads out. But if we do the same thing for neon and do it in the liquid form, actually, it's going to be less dense as a liquid. Does that make sense? Because they're spread out more. Okay? So that would be a liquid. If you notice, they're kind of moving around one another. Liquids, they can move around one another. Okay, and then I'll show argon. Now argon's moving a little bit faster. Okay, not sure why, but it is. Here's oxygen. There's a little bit more interaction between oxygen, and in the gas phase is here. Okay, more spread out. So the last thing I'll have you fill out on that sheet, if you guys look down below, look at those boxes. You can fill out all the boxes except for the last one. So where down below it has particles arrangement, just write out what their particle arrangements are like. Type of particle motion. So here's a solid again. Their motion, what do they look like? Okay, here's a liquid, motion looks like. And then here's a gas, what they look like. And then the last one, the what's called intermolecular attractive forces, we'll talk about what that is later on. Okay. On tomorrow, you'll come in, you'll be given the quiz. I think it took the other class about 20, 25, about half the class to finish it. And then I'll have a little exercise for you guys to do after you're done with the quiz. Okay?